Okay, hi everyone. In this video, we're going to go over using Python, SymPy in particular, to tackle calculus problems. So we're going to look at taking limits, taking derivatives, and integrating functions, okay? So let's get started. Right, we're going to tackle this particular problem where we've got this function, f of x, and we see our variable x on both sides, but we've also got two unknowns. We've got the variable a and the variable b on the right-hand side of our expression. And then we've got two questions. The first essentially allows us to find a and b, and then the second, we take some limits and we take some derivatives. To be able to do the first, as well as to be able to find a and b, we're going to also see how to take derivatives, okay? Because we essentially have two equations written down that allow us to find our two variables a and b. So let's go ahead and get started. I'm going to create a new notebook. I'm going to call it calculus. And to be clear, I started off already in my CFM notebooks directory, where I can see my previous notebooks. And I'm in calculus, and we're going to get started. So we're going to start off by importing SymPy. But what we're doing here is importing it as sim. This is called an alias. There's more information in the book about that. And this should only be done in cases, so this allows us to not have to type all of SymPy every time, but just to type sim. The typing is not really what's important. It's more the reading. It just shortens what we have to read. And that's not always a good thing. Normally, short variable names is actually bad practice because it makes it harder to understand what's going on, unless there really are conventions for these things. So I could, for example, import SymPy as S. That would be silly, even though it would be very, very short, because no one really knows what S means, whereas sim is a very well-used convention. Anyone who uses SymPy is used to seeing that. So we're going to do that. And then we create our symbol. So we create the symbol X, like this, the symbol A, like this, and then the symbol B. We can take a look at them just to make sure that they all look right. Yeah, we got a variable there, sorry, a symbol there and a symbol there. Now, the first thing we're going to do is write down our expression. We could just go there and copy this code, but I don't recommend doing that. I mean, in general, I do. Human error is the whole point of using computers, to remove human error. But when you write things, you are going to make mistakes. So it's good if I'm going to write this out, as painfully as it is to watch me type out a long expression on a computer. I'm going to write out because hopefully I make a slight mistake along the way, and you'll get to see me work that out. It's very normal to make mistakes when you do these types of things. So we've got, that is, I'm going to be looking to the right because I've got it written there. We've got it's 24 times x times a minus 4 times x plus 2 times a minus 8 times x times b minus 4 times x. And all of that is divided by b minus 4 times x raised to the power 4. If we take a look at our expression, we've got 24x, a minus 4x, it's actually taken the 2 directly inside, even though I hadn't done that. So it's 2 minus 16x and b minus 4x over b minus 4x squared. Okay, now we're going to calculate our derivative. So I'm going to create a variable derivative, and I'm going to assign it the value of SymPy's diff function. And diff takes an expression, diff tool, and diff takes an expression and the variable with which we are differentiating. So df dx, we get that. And so if I take a look at the derivative, it's equal to that, which is fairly well, messier than we would like. So let's factorize it just to take a look at it, see if that simplifies things. At this point, we don't actually know if this is going to do anything, but it takes computer no time, so we'll go ahead and do that. Sure, it looks like something. Okay. Now in the problem, we had that when we differentiate f with respect to x and substitute x equals 0 into it, we should have the value 0. So we're going to write down that equation. I'm going to call it first equation. And so we create an equation object where the left-hand side is going to be that derivative when we substitute a value of x equals 0, and the right-hand side is 0. So if we take a look at that equation, we get that. We can factorize equations as well. And so we get that. We can already kind of see what the relationship between A and B is going to be. But let's go back to the tutorial and see what we're doing next. The next part is to get the second derivative, okay? And so we're going to use that diff tool again, but the only difference is we have to add another variable, which essentially by default is always 1, but is how many times we want to differentiate. So second derivative is equal to sim.diff, the expression with respect to x, but we want it twice. We could, of course, just differentiate the derivative as well, but we can get the computer to do it all in one go. So take a look. That's the derivative. Again, for better or for worse, it's not incredibly clear what it is. We could factorize that, etc., but we won't. We'll just keep on moving. So we'll write down our second equation, which is a SymPy equation, and it is our second derivative. When you substitute in a value of x equals 0, we now get a value of -1. And there we go. That's our second equation. We're going to go ahead and solve our first equation using the solve set, using, solving it for A, so that if you look there, you can probably already see what A is going to be. A is indeed B over 3. And now what we're going to do is we're going to substitute that value into our second equation. So our second equation, we're going to overwrite it, so assign it a new value, which is our second equation, our present value, where we substitute in A is B over 3. Because B is already a symbolic variable, we don't have to do sim.s here like we've had to do in the past. As it's a symbolic variable, it'll treat B divided by 3 as a symbolic variable. And that's our second equation. And so now we're going to solve this for B. And so we get 4 values of B. 2 of them are imaginary, and 1 of them is negative. And so we know that that is indeed our value of B. In the question, it said that B was a positive number. So we're going to go ahead and update our expression to be our expression, our current expression, which has the A's and the B's in it. But we're going to substitute A to be this thing here. So, well, A we know, pardon me, is B divided by 3. So it's going to be all this divided by 3. So that's 2 times the square root of 2 multiplied, and now we need the 4th root of 3. So we'll use the generic tool root, which takes the value, so it's root of 3, but it's the 4th root of 3, and we divide that by, indeed, 3, because A is B over 3. We also have, we don't just want to substitute that, we also want to substitute the value of B, which is just the same thing, but without the 3rd. Okay, so here we're separating the value of A to the left of this comma and the value of B to the right of that comma. And so now if we take a look at our expression, there's no A's and B's, it's just that, okay? We can confirm a couple of things, so we can say, all right, give me the derivative of my expression with respect to x, and substitute a value of x equals 0 into it. We do indeed get 0. And if we differentiate our expression twice and substitute x equals 0, we do indeed get -1. So it looks like we found the right result. So going back to our problem, then we're asked to find a couple of limits. So the limit as x tends to 0, the limit as x tends to infinity. So let's do those. And we do those by doing sim.limit, so SymPy is limit. We take the expression, we say the variable we want to take the limit of, so x is the variable that's moving, and we want x to tend to 0. And if we do that, we get √3/36. The other limit was as x goes to infinity. And I don't actually like the way they've done infinity in SymPy. I would have preferred to just have sim.infinity. The way they do it is to look like the sideways 8, the infinity symbol, and they do an O. So that's not the number O. Actually, that's very obvious, but it's just O. And if we get that, we get that the limit of that function is 0. So in the last two parts of this problem were to get these two integrals. Let me just scroll down so everyone knows where I am in the tutorial as we're doing that. And to do that, we use the integrate tool. So it's sim.integrate, and we take the expression and we say the variable we want to integrate by. And the very first question was just the indefinite integral, so there's no limits of integration. And if we do that, this one takes SymPy a little bit of work, but that's the expression we get. We could, of course, factor that if we want to try and tidy it up a little bit. So let's go ahead and put that on top or expand it or whatever. And sometimes in practice, you end up kind of experimenting with these different things just to see what's most helpful. And then finally, the question was to get the integral between 5 and 20. So I'm just going to grab that code, copying and pasting, as I said, to try and avoid doing. And now instead of passing a variable x, we pass a tuple. And that tuple is going to be those three things. So it's going to be the variable, the lower bound, and the upper bound. And then if we run that, we will get a number, an incredibly messy number. And if I extend my window a little bit and rerun it, should tidy it a little bit, but it is a number, okay? And so I could go value of integral, value of definite integral. And then I could, for example, if I want to get an approximation of it, see that that's what it is. And that's essentially what we've seen here is how to do those three things and answer that question. So after you've gone through the tutorial, please go through the how-to section where we look very specifically at calculate the derivative of an expression, calculate the indefinite integral, calculate the definite integral, use infinity, and then calculate limits, which are the various things that we've done. Then there are exercises and solutions, and finally some further information if you want it. So yeah, good.